So, not sure if I'm going to be too late to help anybody, but and it's probably going to take me a long time to get all these chapters out, but this is 3.1. If you spend some time looking, you're going to discover 3.1 is all about the derivative of distance graphs. And it's going to look at the derivative of distance graphs is going to come out with a velocity equation. And the derivative of velocity is going to come out with an acceleration equation. So you got to get into your first derivatives, which is just the derivative of your function, and your second derivatives, which is your derivative of your first derivative. Second derivatives are interesting. They will tell you all sorts of where your graph is going. Generally speaking, if your second derivative is 0, you're hitting an inflection point, which you'll learn more about, which means your graph is going to start changing whichever slope it was doing. And for instance, when the second derivative is negative, you're always talking about a concave up. And when your second derivative is positive, you're talking about a concave, that was concave down, this concave up. And your first derivative, when it's 0, indicates a critical point, or turning point, sometimes called maxima and minima. And these things are going to be very useful for graphing. So it's taking you to the next level of graphing for rational functions and polynomials. But in this case, it's all about physics. And so if you look at here, they go through what's what about velocity. Negative velocity indicates an object is moving in a negative direction. So the other thing you got to think about graphs is when it's going up in a distance graph, it's moving away. Consider the baseline as home, I guess. And when it's coming back towards baseline. So when velocity is positive, that just means the slope is positive, so it's going up in the interval. And when velocity is negative, i.e. the slope is negative, it's coming back down. Positive velocity indicates that an object is moving in a positive direction, or up or to the right. It depends what they're talking about. Zero velocity indicates that it is stationary, i.e. you'll see a critical turning point. Second derivatives are often this, f double prime, or this, or this. But f double prime you'll see a lot. Negative acceleration indicates the velocity is decreasing. So as I said, it indicates that the object is starting to turn around. Positive acceleration indicates the velocity is increasing. That's not really big news. And zero acceleration means that the velocity is constant. So acceleration, as you know, when you hit the gas on your car, just means you're changing, the rate of change for your velocity is changing. And that's all acceleration is. And it's in a term called meters per second squared. And that's because when you first measure your distance versus time, it's meters per second. But when you then, and it's called velocity, but then when you measure your velocity versus time, you're measuring how fast that velocity changes per second. Once you rearrange these units, you realize it's meters per second squared. And that's acceleration. And you're going to see it in physics a lot. And there's some derivations I can't even do for the physics. The physics is deeper thinking. This is stuff that you don't necessarily know. Velocity and acceleration have the same signs, then they're accelerating or speeding up, and when they have opposite signs, they are slowing down. I think that's kind of pretty obvious. And the speed of an object is defined as the absolute value of the velocity times the time, the velocity based on the time, which just means speed is always positive. We don't think of negative. You're moving negative 50 kilometers an hour. You're moving 50 kilometers an hour. Too much time spent on the prerequisites, and so I'm not going to do it anymore. You need to be able to realize which graphs these are. This is lines. This is lines. This is a radical function. It's a radical function translated 2 to the left. This is an upwards facing parabola, and that's a downwards facing parabola. The sooner you can recognize your functions, the better. Use your decimals. Play around with your decimals. Then they want you to expand, solve for x. They want you to get used to expansion. They also want to get used to these fractions, which really bother a lot of kids. And the secret here is finding a common denominator between 2, 15, and 3. And we're pretty much talking about, looks like 20. Nope. If we multiply them, it's too big. I guess 30. Go with 30. So you're going to get, this is going to turn into a 10. and this is going to turn into a 6, and this is going to turn into something 15 times that. But be aware, you're doing it once on the left and once on the right, so the 30 applies to both of these things, and once to this. This is still an upward-facing parabola, and so is that. And you should be able to factor those. This is a rational function. If you got them all on the same denominator, you'd find that t squared's on the top, and it's probably a line. Now, to solve this, it's not a bad idea to multiply the left side and the right side by t, and you're going to discover that you have t squared up top, and t and a number and a t on the right. And it's all loud, or you could, if you want, just remember that t can't be equal to 0 in this case. And here's a cubic. Always know that your cubics, where they start, where they end, whether they're downward facing, and always also be aware of your y-intercepts when x is 0. And this is a quartic. And remember how many turning points they have. Solving inequality is tough. Learn it. You won't need it much, but it helps to realize that you're going to be facing a number bar, and your inequalities will either be between 2 points or outside the 2 points. And when it's between 2 points, you can just say the number, let's say that's the number, is smaller than x is smaller than that number. So it's in between. We'll be seeing that, don't worry. Get used to your areas, how to do a circle, etc., etc. How to analyze backwards. How to calculate surface areas for cubes. It's a dice. It's a 6-sided dice, 6 sides of squares. Get back into your notation, your interval notation. Learn what that means. Remember what the circle, the rounded bracket means. Use your Desmos. It's a fantastic tool. Then they just explain that the derivative, second derivative, is acceleration. They try to get you out of the notion of how something moves. And they just discuss analyzing motion and what it means. So my biggest recommendation for you is recognize your graph, first and foremost. Okay? Explain the difference of velocity in times of t1 and t5 for this. Okay, so these are warm-ups. Part A is always warm-up. Part B is more likely what's on your test, and Part C is challenging. From now on, I'm not going to do Part C. I'm going to focus on mostly Part A and B. And I'll discuss C at times. So T1, T2. So what kind of graph is this? Rearrange it the way it should be. This is a downwards facing parabola. So that's minus t squared plus 2t. Sorry about my writing. I do it because I'm fast. And if you want to get a little bit of information about it, keep this for derivatives. But if you want to quickly analyze it, you're going to discover that when you take out minus t, you're going to get a lot of information. In other words, we're facing something that at 0, 0, and 2, 0, it is doing that. So obviously we got a lot of automatic information about its vertex, because I know that 1 falls between 2 and 0, and that it must fall between those 2 points. But they want to explain the difference in velocity. Now here's what's interesting about this. This is already a velocity equation based on distance. It's usually this. So already we can tell at 1, because this is a vertex, its acceleration is 0. Because you can make a big mistake and consider this a distance graph, and then you'd go, oh well, at this peak the slope is 0, therefore the velocity is 0. But no, this is a velocity graph based on time. So you have to punch in 1, and you're going to discover it's 2 minus 1. It's equal to 1. It does indeed have a velocity of 1 meters per second. And then at 5, you're going to discover it's moved past this point, and it's downwards. Now the interesting thing at 1, because I know it's a critical point, is the acceleration is 0. If I were to take derivative of this, I'd get minus 2t plus 2. At 1, minus 2 plus 2, 0. And that's because this derivative here would produce acceleration, which means this car is stopped, and its its foot is off the gas. It's about to come back towards target. Now, a downward slope afterwards, it's negative velocity, so it is now heading in the other direction. just remember that once it hits 0 here at 2, on the distance chart, that would represent the turning point on the distance chart. So clearly at that point, it's actually heading back. Okay, so at 5, when you punch it in, you're going to get 10 minus 25, which is minus 15 meters per second. Explain the difference and discuss it. What's going on? Well, not only do I know it's already past the x-axis, so it's now coming back towards home, but then negative velocity means it's accelerating in the other direction now. I shouldn't say accelerating. It's moving in the other direction. Okay, let's see what's next. And sorry if I get some of those wrong. Really, I am more about the problem solving. And sometimes I rush because the chapters are huge. Determine the second derivative. Very good. So some of these are easy. Got to follow the same rules. 10 comes down, x to the 9, 6 comes down, plus 18x to the 5. Then you do it again. 90, x to the 8, plus 90, x to the 4. This would be marked y double prime, and this would be marked y prime, and you want to write it clearly and keep it somewhere in the corner for when you need it. This one, so if you can't follow along, because we were doing tons of derivatives last time, it's just the derivative of the derivative. So that's really this, which is really this. And normally I would now put this at the bottom as a square root of x, except now we got to take the next derivative. So that's f prime right there. So now I take f double prime. That's going to be this. What happened there? The half came in front, the negative a half, and multiplied that. It's going to get lowered by 1 even more. Okay, so there's the second derivative. You might leave it in that format, which will help you in equations, but not in the calculator. Or you can also write it like this. This negative just means the x is down here, and it's x cubed, and don't forget your 4. And this is the cube, and that's the square root. Get used to your exponents. So that's the second derivative right there, but so is that. This one's going to follow the chain rule, right? Or they call it a variation of the chain rule. So the first derivative is this. And keep in mind the derivative of the internal is not just 1, it's minus 1. So you just put it up front, because this minus 1 will affect the outside. So that's the first derivative. And the second derivative is quite nice, because if I want to expand this, I get this, right, because it's now to the 1. So the second derivative is simply this. A lot easier to figure out. And if you wanted to do it internally without expanding it, you just focus on that, minus 1 times the minus 2, and you still get plus 2. That second derivative is quite smooth. Oh, this really? Come on. You don't need me for this. Bring it down, multiply, lower. Bring it down, multiply, lower. Bring it down, multiply, lower. Gone. This is now just 1x. Then bring the next one down, multiply, lower. No, I'm not doing that. Come on. Yeah, they're just making you practice your fractions. And yeah, no wonder it gets confusing. So when this comes down, it becomes 6x, and this becomes to the half. How did that happen? Well, the 3 multiplied by the 4, 12 divided by 2, 6. And this comes down, makes it positive x to the minus 3, and that's positive 2. Minus 2 times minus 1. Okay, and the next derivative, so try to remember that this is a half, that's why note taking is better. So now this becomes 3x to the negative half plus, minus 6x to the negative 4. Now notice this sign switch back and forth. So that's it there. That's the second derivative. Here is quotient rule. And before you ever use the quotient rule, make sure there's a term up top and a term at the bottom. So the quotient rule says it's going to be 2 times times the bottom. So the derivative of that, and subtraction, use your big brackets. And this is derivative of that is just 1, so it's minus 2x all over this squared. Right? Now, resolve this before you get it. It's 2x minus 2x. It's just going to be 1. So some of them you always want to watch and make sure it can be resolved easily enough. Okay? Now, this is no longer the quotient rule. This is the same as this. So the derivative of this is the chain rule now. So that's first derivative. This is second derivative. 2 comes down, the contents stay the same. 2 gets lowered to -3. Then the derivative of the contents, that's just 1. So there's the second derivative right there. If you're to readjust it, this whole thing goes in the denominator, but you don't need me for that. Okay, you have 2 choices here, and personally, it's not too bad to leave it separate. But once you get to the bottom, it would be a good idea to get this on the same denominator. And you're going to find you need to do that for other things. So remember that this thing is just over 1, and this is a different denominator, and to add them, it's like any rule fractions. So if I wanted to rewrite them, it would be this. What? Well, think about it. To get this over x2, I have to multiply this by x2, making x4, plus 1, and now it has the same denominator of x2. This is the same number, function, fraction as this. So in this state, I can just use the quotient rule, but in this, I actually prefer doing it in this state up here, because then I only have to do the power rules. So here's the first one. What? How'd that happen? Because when it comes up, it's x to the -2. The -2 comes down, lower to -3. That's the first derivative. Second derivative. This one's nice. Second derivative done. So like this, it's really easy. When I rewrite this, though, it's going to look like this. So obviously there's some new conditions to this. Well, they were there too. And if I was going to rewrite this on the same graph, it would really be this, on the same denominator rather. If you can't see what I did here, oh, yeah, I got it. If you can't see what I did here, and this is to the power of 4, by the way, then think about it. This one, you just put it to the half. You don't need me for that. We did a few of those already. This one's the chain rule. It's just twice. So I'm just going to do them. Feel free to comment if you want clarification. And this is the reason I'm racing through these is this is chapter 2. We're trying to get through to chapter 3. Oh, sorry. So this is the first one, and then I also have to multiply it by the content. So that's going to become 6. So that's the first one. And the second one times 2 is this. Now, yeah, you could expand it. The textbook, for some reason, likes expansions. Expansions are fine for simplifications, but for working formulas, no need to expand. This one, the secret is, it's actually pretty easy, this one. Just you got to remember your exponents. This is the same as this, as you probably know. So the first derivative is this, because when I subtract 1 up here, that's what it becomes. And the second derivative is this. Done. Practicing your derivatives is probably one of the best things you can do. To be very honest, I'm not that good at them. But the basic ones you can get fast, it saves you a lot of time. The only thing I would caution you with is watch out for confirmation bias, where you think you're so good at derivatives you don't have to check your work. Always check your work. Each of the following position functions describe the motion along a straight line. Final velocity and acceleration, so notice they're all distance. So they just want us to take the derivatives again. And really, This one, come on. 10t minus 3. That's velocity. So I'll do it again. That's velocity. And notice the acceleration? Constant. This thing is always accelerating 10 meters per second, or they didn't tell us. And its velocity is this, which is a straight line, which is why its slope is a constant. Always recognize your graphs. So you'll notice whenever we have a square, this is going to be the scenario. So whenever your distance is a parabola, your velocity is going to be a line, and your acceleration is going to be a constant. Good little tip, that one. What are we dealing with here? Cubic. If I was to graph this, I know it starts in quadrant 1 and possibly does something like that. First derivative. Notice that the first derivative is a parabola now, so at most it has one turning point. There's only one spot where the acceleration is going to be 0. And notice that the acceleration is now a line. Velocity is a parabola, and the distance that this thing is going is a cubic. So they're still, they're going to be limited by their same rules of functions. It's why we learn the functions. Oof, that's a tough one, isn't it? Sure is. So if you wanted to put these all in the same term, you would multiply them all by t, these other two. In the first one, you'd get t squared over t, and you say, why would I do that? Well, wait a minute. The next one, you get minus 8t over t, and I'm not changing them, I'm changing their denominators. Notice their denominators are the same now. Now you get a good idea of what's going on at the top, and a good idea at the bottom. So if you take most parabolas, if they cancel out, I'm just going to keep that one because it's this thing here is better for the derivative, and this thing here is better for understanding the graph. So if you ask to graph something, try to do this. So if you imagine a parabola with these conditions, I don't think it crosses the x-axis with these coordinates, but it's upward facing. So if you imagine that, and then you realize that t is in the denominator, that means at t is equal to 0, it's going to have an asymptote, which means this parabola is never gonna get there. And it's probably going to go down here and up here, or it might be going way up. So what you should do is measure right like negative 0.0001 and positive 0.0001. But this, if it doesn't cancel out in the above factoring, is going to create an asymptote. If this cancels out, you're going to see a normal parabola with a hole in it. So remember your functions. Now, I'm going to go back to this thing. First derivative, let's rearrange it. I'm going to get t plus 6t to the minus 1, minus 8. This 8's almost useless, right? First derivative. Actually, he should be first. First derivative, 1 minus 6t to the minus 2. So that's good to know. And then this one's going to, that's velocity. Second derivative, plus 12t. So this plus is way too big because it looks like a t. And that's the second derivative. If I was to rewrite it, that's it. Get a number over t cubed, which would normally be that. You're going to see a very, I can't visualize that right now because it's 1 in the morning. Oh, which one was that? Okay, I did that one. Oh, this one's crazy easy, so I don't think you need me to do it. First derivative. Expand it. So that's velocity there, and here's acceleration, constant. And you see that? It's kind of nice and easy. Because if you were to expand this, what would it be? A parabola, who happens to have a vertex at 3, 0. So the velocity is going to be a line, and the acceleration is going to be a constant. Okay. rewrite it. So that's still distance. Velocity is this. What's the derivative of the content? Just one. Acceleration is this. Follow the same rules that you learned in Chapter 2. Understanding what this is actually this. The negative sends it down. The 3 is a cubed to the whole thing. The 2 is a square root. It'll look very odd. You have a line that's going down divided by a square root. I'd like to see that. Quotient rule if you must. If you really want to save some time, you can also probably get away with the product rule in this case. However, if you do the product rule, you end up with the several chain rules. So let's just try it with the quotient rule. The reason I don't like the quotient rule is this minus can really screw you up. Notice our t's are going to cancel out. 9t minus 9t, I'm left with this. So that's my velocity, my acceleration. This is no longer a quotient rule, it's really this. Don't get confused with that. So bring that down. That's my acceleration. Okay. Next, and the reason I'm storming through this is because I'm aware some kids have exams coming up, and this is a virus year. I really meant to save some kids some trouble this year and just help them out with free help. Keep in mind, these questions aren't to cheat. They're to verify that you know what you're doing during a test. And the more you can do these, the more you can repeat them, great. So assuming that these are all position versus time, which they are, when is velocity 0? When the slope is 0. Here and here. When is the object moving in a positive direction? Here. When the velocity is positive. When is it moving in a negative direction? After the peak. Here. When the slope's negative, it's moving back towards the home. So here, positive. So there's an interval from here to here. And from here forever. So if I was to write down the intervals, it would be, this one has very fixed intervals because it stops here. So it would be, the interval would be written like this, and I'm assuming it include the graph here. It would be square to say I include it, 1, comma, 3. That's the positive direction, and the negative direction would be square to include it, 3, 5, square. And that's the negative direction. Positive direction, there's 2 here. Square, 1, comma, 3, square, and square, 7, comma, positive infinity never has a square. So that's positive. Negative is just from here to there. So you get square 3, comma 7 square. I just want you to read your graphs. Learn how to read your graphs. Ooh, particles. Yuck. I actually like physics until you get really into the, you know, when you realize that things aren't just simple acceleration. Like particle acceleration has so many components, so many constants. So what kind of graph is this? It's a cubic. You could make it simpler by factoring out a third, and you get a lot of interesting things. Determine the particle's velocity and acceleration at any time. When did the motion particle change direction? That's when it is at a v is equal to 0. When did the particle return to its initial position? When this is 0. Okay. Figure out a couple things always. What's the position at 0? Notice they all have t's. What's the position when t is 0? 0. So at 0, 0, it's starting. What's the velocity here? We don't know. We'd have to take the derivative. So let's work on the first derivative. What happened? 3 came down. Resolved. So the first derivative is a parabola. Let's work on the second derivative. The second derivative, acceleration, is a line. So you're going to see a thing like that with a slope of 2, which means its acceleration is not a constant, but it isn't change. Well, I guess it's changing. It's a consistent change of velocity, I guess, is what you would say. When does the motion change direction? Well, when this is equal to 0. So we're going to factor it. Oops. Those are the factors. So it is clearly changing directions twice, and we need to, you would then take a second derivative to figure out when that is, and I'm going to show you that right now. So it's changing at t is equal to 3. So you punch 3 in here, you get minus 18 plus 9. Oh, what am I doing here? 3. Well, I guess you can just say t is 3 and 9. You don't need the distance. But now, put the 3 into this, and you get 6 minus 4. So it's positive, right? So I can tell you right now, that's an upward facing concave up. Punch the 1 into here. You get a negative number, right? I can tell you right now, that's a downwards. So if I was going to plot this, I could tell you right away at 1, right here at 1, wherever it ends up being. So at 1, it's a third minus 2 plus 3, so it's plus 1. It's 1 and a third. So 1 and 1 of the third, because it's negative, I can tell you it's, and we go through origin. It does that. And then at 3 seconds, I'd have to plug it in, but it looks like it's going to be way negative. It's close. I can tell you it's going up again. Now I could figure out where it's crossing the x-axis by factoring something out here, and it's sometimes worth it. And when does the particle return to its initial position? I think we're going to find 2 spots there. So that means take your initial graph. By the way, those were the 2 times. At t is equal to 1 and t is equal to 3. It's the factors of velocity. And for this, always look and be careful. As soon as I see the t's in there, I know t can come out. Now I'm also going to factor out the third. And you might be confused by this. Oh, third t. And you might be confused by this. Watch what happens. So, what's factoring? Well, you're essentially dividing everything by the thing in front. And if you look at it visually to get rid of it, it's like multiplying it by the reciprocal. But instead, if you think of it as dividing by a third, what's 2 divided by a third? Well, know your fraction rules. That's the same as 2 times 3 over 1. You must flip that upside down. That's 6. If you don't believe me, grab your calculator and ask it to divide something by a third. Whenever you divide a number by a number that's less than 0, the result goes up compared to that number. It's bigger than that number. So it's clear there's factors here, and it's very clear which ones. Okay, so at 3 seconds, it does a bounce. So remember when it had that turnaround at 3? So this is what it looks like. Here. And then at 1 and 1 1/3, I think it was, does a turnaround. And it does a double bounce right there. Thump. And this side of it, it's going there. You're very rarely concerned about the left side of time. And then right there, 3, 0. Okay. That also happens to be the turning point when velocity was 0. A lot of information from analyzing that. And sometimes in a test, you just don't have the time to do it. B's are always a little bit harder, but it's just really more number hard than concept hard. C's are hard. I agree that C's are hard. And as we get more into this, even I have to admit that I'm really here to help you understand the concepts, but some of those puzzles in C, I have to go back and revisit. So we're talking about an object, straight line. So I want to know if it's moving in a positive direction or a negative direction at 1 and 4. So to find that, you really need to find the slope. If it's going like that, it's moving in a positive direction. If it's going like that, it's moving in a negative direction. And one might argue that the acceleration has something to do with it. But let's just find all the derivatives, okay? Okay, derivative of this one. That's the first derivative. Notice it's a line. Derivative of the second one, it's just a constant. So in this one, let's look at the time 1. Well, I know at time 0, it's 4. And time 1, it's going to go down by 1/3, but up by 1, so it's going to increase. So I already know it's increasing. Plug it into here. I get minus 2/3 plus 1. That's plus 1/3. So that means its slope, as it's climbing, right there is 1/3, which is a positive direction. Even here you can see it's moving away positively. Okay, what about 4? Okay, it's clear from 4 here. You get minus 8/3, which is more than 1. And the result is going to be minus 5/3. So now it's gone over that peak and it's coming back. And where is that peak? Well, when this is 0, you could easily figure it out. It's minus plus 3/2. So 1.5 seconds. What about this one? If you were to expand that, what would you get? Well, the brackets expands to a parabola. When you multiply it by t, it's a cubic. And you know what? If you really want to make this a faster expansion, yeah, well, thankfully this is just t, so the first one, yeah, well, we're going to have to do the product rule. If you want to make, you can make your life a little bit easier sometimes if this is worth it. And then when I multiply through, boom, I personally now find this derivative easier to do. By the way, what did I do there? I expanded that and then multiplied everything by t. And I got t cubed, so already I made a mistake right there. So I might as well go slowly. Still going to do the expansion though, because it's a lot easier than doing the product rule. If I were to expand this, this is what I'm going to get. Now all I got to do is, sorry, there we go. Now all I got to do is run the t through it, this t. Great. Cubic. But using the power rule is a lot easier than using the quotient rule. So now its velocity is this. And at 1 second, this is 3 minus 12 plus 9. It's 0. So it's neither moving away or towards. It's a peak. And if I took the second derivative, I'd actually figure out if it's a valley or a peak, but it's probably a peak. Well, it's a good question. We can always take the second derivative and figure out the second derivative of that is that. Yeah. And then at 1, we see it's negative. So it's a, yeah, so it's a peak. It's a downward facing. A negative acceleration at the time will tell you it's downwards. A positive will tell you it's upwards. Okay, what about at 4? Okay, well, this is 4. 16 times 3, 48. 4 minus 48. There it is there. Positive 9. So it is going somewhere like that. And you could figure that, the acceleration out there as well, if you wanted to make sure. You don't need me for that. It's the same thing. It's the same technique. It's a cubic as well. Notice that most of the distance ones are cubics, and well, actually, you'll get some interesting ones. Let's see, do I remember it? No, of course not. Why would I remember it? Straight line. What is the velocity at time t? It's the derivative. By the way, t is 0. It's already got a distance. It starts 8 meters away. And its velocity formula is this. So it's a line. When is it velocity 0? When t is 3 seconds. And this just means find the derivative. When it says at time t, it just means find the derivative. I guess I missed all the questions on this one. Yeah. When does it stop rising? What is the maximum height? Okay. That just means when is its derivative 0? Rearrange it always. Just helps you understand. So the derivative is this. So when is that equal to 0? Rearrange, rearrange, rearrange. When time is 4. What is the height? 40 minus, well, 40t. So 4 times 40, 80. 160 minus 16 times 5, 80. The height is 80 meters above the ground. So that height, the coordinate would be 4, 80 is the vertex, because it's a downward facing parabola. So these are pretty child playish, and they're just trying to train you. But you can kind of see that it's pretty child playish. So the last ones are hard. So take the derivative, then plug t in for 5. Rearrange again. Jesus, why do they keep trying to do that? The derivative is this. Then plug in for 5. So they give you a time, so you plug it in. So 10 minus 7, 3 seconds. So determine the velocity, not 3 seconds. It is 3 meters per second. That's the velocity. Determine the acceleration, second derivative. The acceleration is a constant. Second derivative, or derivative of this, is 2. So the answer to this, anytime, it's always going to be acceleration of 2 meters per second squared. That's always acceleration. That's always kilometers, unless they give you like kilometers per hour or something. But I mean, it's always meters per second and something per second squared. These are softball. And it's to prepare physics students for the future. Now, usually when it has an A on it, it's like, watch out. The secret here is you could easily think this is a parabola, but it is not. Okay? Looks like a parabola, but that's a 5 to the 2. So 5 to the 2 is the same as a t to the power of 5 with a square root on it. Calculate the object at time t. So that just means take the derivative and the second derivative. So here's velocity, and here's acceleration. Now, personally, I think it's a lot easier to take the expansion. However, the derivative of that is pretty easy. So looking at the power rule, the product rule rather, screw it. Let's expand it out. Try to keep in mind that this is t over 1, and that this is a fraction over 2. So you can just say this is t, 2 over 2. When I expand this part, I get 7 t to the 5 over 2. When I expand this part, you're supposed to add exponents. So 1 on top of that, that's minus t to the 7 over 2. Huh? Because it's over 2, 1 whole unit is 2 more up here. So that's the expansion, which means the velocity, if I rearrange it, is, I subtract 1 from that, plus this comes down, I get 35 over 2 t to the 3 over 2. So I got a 5 over 2 here, and a 3 to the 2 here. Then the acceleration is the same thing again. Might have been easier to take the, So anyway, the acceleration is this. And then calculate time t. How many seconds does the object stop? After how many seconds does the object stop? Well, one thing I noticed, that distance here at one point here, at 7 seconds, it is hitting the ground. So that's important to notice. Another thing to notice is that it starts at 0. So when does the motion of the object change direction? And how many seconds does the object stop? So I think they're first saying, when does this equal to 0? And that's an interesting one. So this one I'm going to have to write a little bit more clearly. So I'm talking about minus 7 over 2 t to the 5 over 2 plus 35 over 2 to the t 3 over 2. I hope I got it right. Actually, before I continue, let me pull up the answer so that we don't waste all our time. Which question is this? 10? Yeah, I think I got it. Here it is here. So we'll just keep it handy. Did I get it? Yeah. Ooh, I screwed up something here, right there. Or did they screw up something? I think they screwed up something. Yeah, they screwed up something. This 3 over 2, when it comes down, the 3 turns that into 105, but the 2 is supposed to turn it into 4. And they didn't simplify anywhere. So I think they screwed that up. But anyway, at least I believe I have my things set correctly. Alright, so how do you solve this? How am I going to figure out when this mess is equal to 0? Well, believe it or not, get them on opposite sides. So this is a minus, so I'm going to just send it over here. So you just add it like as if it's a number. You just treat it like a number, and when I add it to both sides, I get this. Okay. Now, I happen to know that this fraction is a bigger number than that one, so I'm going to keep this on this side. I'm going to get rid of these. So I'm going to multiply it by the reciprocal on both sides. Look at some lovely things that happen here. And now that has effectively destroyed that. And now I'm going to get that 5 all alone on its own side. So I'm going to divide by t to the 3 over 2 on both sides. And here's where another lovely thing happens. What's the rule of exponents? This exponent minus that exponent. Guess what that equals to? T to the 2 over 2, which is the same as just t. So we discover that when t is equal to 5 seconds, the velocity stops, which means this object goes up and comes down. And so right there, it stops. So we have an object that starts at 0, right here at 5 seconds, and then it plummets and hits the ground at 7. What does the motion of object change? When does the motion of the object change directions? So that would be, I believe that's at the same time, unless they want the inflection point. I mean, you could set the inflection point to equal 0, go through the same rigmarole. Is that what they want? No, they're just talking about 5 seconds again. Well, yeah, of course, when it goes up, right there, it's changing its direction. What is when is its acceleration positive? Well, that's an interesting one. So when is this thing over here positive? Let's figure out when it's 0 first. By the way, when does the object return to its original position? Definitely 7. And since 0's over here, I believe it's 7 and 0. And again, let's just see the answer. Yeah, after 7 seconds. Alright. So, let's make these equal. This is negative, so let's put it on the other side. And keep in mind that I made them equal to 0. And the secret is, when it's below 0, it's going to be negative acceleration. When it's above 0, it's going to be positive acceleration. So we're just essentially trying to find when is it above 0. Okay, so it's the same rule. I'm going to multiply by the reciprocal. Lo and behold. 3. Unfortunately, in real science, these numbers are never smooth. And I'm going to get the number alone by dividing on both sides. It's going to cancel out on this side. And look at that. That's left with t. So, at t at 3 seconds, since I know it's going up and coming down, I believe that at 3 seconds, after 3 seconds, we're going to get a negative thing. So I'm going to put 3 down. I'm just going to bring back my original stuff. And hopefully I still have it. There we go. And I'm going to figure out like 2 seconds. It's going to be on either side. And I believe it's when it's above 3. 'Cause that would make sense. So right there is when the acceleration. Yeah, I don't need to do that. Since it's heading up, that's the inflection point, and it's turned around and come down. Let's confirm it. Oh, I got 6. Now, I think they used their 2 in their equation, which would explain why they got 6. But I do not believe it's the truth. So t to the 5 over 2. It's to shift 6 to get your exponents. 7 minus t. And I love this tool. And, oh yeah, keep in mind that I just convert to x because it can't handle. So I'm just going to take the ask it when is f prime 0. So that'll give me my peak. Woo! Yeah, I forgot it's way up there at 80. There it is. Ooh, I got the wrong height in the calculation. And then, oh no, I didn't do the height. And then I'm going to set 0 to the second prime. And I'm going to get rid of that. I don't really need the first one. So they get, yeah. So, see, we got it right. They got it wrong. Because everything after that, if I put in f double prime of 3.1, it's negative. 3, it's 0. 2.9, it's positive. So they got it wrong. So we got it right. So the inflection point is right here at 3, wherever f of 3 is. That's 62. Somewhere in there is the inflection point where it starts turning around. So it's good to know that we did the calculation right and they did it wrong for probably the first time in all these videos. Ball's thrown upwards. It's a downward facing parabola. Nope. If they're a repeat, I'm not going to do them. So, calculate the ball's initial velocity. So this is given by height. So the initial velocity is when t is equal to 0. And this is the first derivative. So obviously when t is 0, the initial velocity is 25 meters per second. Meters per second. Calculate its maximum height. Okay, its maximum height is when this is equal to 0, which means 10t is equal to 25, which means t is equal to 2.5. Plug in 2.5. By the way, I could have found that by just factoring out minus 5t, and then there would be a t minus 5 in here, which would tell me between 5 and 0 is when it hits the ground. 2.5 is its height. And then when I do 2.5 here, I get 5. What do I get? This is where I would just plug in decimals. Anyway, you take the 2.5, plug it in, it'll give you your height. When does the ball strike the ground? Well, I just told you. But now we take 5 and we plug it into this. So we get minus 50 plus 25. So it's minus 25 meters per second at time is equal to 5. When it hits the ground, it's going minus 25 meters per second downwards, which is pretty damn fast, actually. These ones I'm not gonna do. I had to look at one of them, and I can give you some tips, but if your teacher wants you to do that on a test, talk with your teacher. I'm not doing the advanced physics questions. Drags a race down a strip. Its distance in meters from the starting line t seconds is given by an upward facing parabola. It always helps if you understand it too as well. So take 2t. So already you can tell that there's a time. You can already tell that there's a time negative a third when it hits, which we never care about negative time, and a time 0. So somewhere here goes up, and at 0, it's downwards. From there on, it's going like that. only cares about this part. When does it cross the finish line? Okay, it's 400 meters away. I'm surprised it doesn't have a plus 400 here. So that means and it even tells you 8 seconds. So you take the first derivative of this for velocity. This is a waste of time. And you take the second derivative. That's the acceleration, so that's always the answer to that at any time. But at 8 seconds, its velocity is 98 meters per second. Good, good, good. How fast was it moving at 60? Well, we have to find out the time for 60. So you set for 60 is equal to 6t squared plus t, 2t. You got 6t squared plus 2t minus 60 is equal to 0. And this is the distance, because they only gave us the distance that it was moving down the strip. Take 6, and I got a 2t there. Take a 6 out of it all. Oh, don't take a 6 out of it all. Take a 2 out of it all. Did I do that right? Let me just... Yeah, I did it right. So I got that plus 2t. Yeah. So is there a factor for minus 180 and plus 1? Now I'm not even sure. Oh, Jesus. Getting old. Minus 9. Yeah, there we go. Minus 90. Plus 1. Yeah, it's plus 10 minus 9. So using 3t, this is the slip and slide method. Sorry. This is the slip and slide method. Now we're going to take this 3. That's t minus 3. This 3 won't go into 10, so you get 3t plus 10. And just to make sure, 3t squared plus 10t minus 9t minus 30. So that means at t is equal to 3 seconds, and this creates a minus time we don't care about, so it's 3 seconds. Now that I have 3 seconds, I can punch it into the velocity thing, and it's 36 plus 2, 38 meters per second when it was 60 meters down. You would always say the object was moving 38 meters per second when it was 60 meters down the strip. For each of the following position functions, discuss the motion of an object moving on a horizontal line, where s is t meters, t is in seconds. Same thing. It's the same stuff. Just get good at it. You know? Practice it so much that when you're asked a question, you can just spend very little time on these easy ones. You're only going to get one of these on a test, because the other stuff's harder. Okay, so yeah, you got to kind of figure out stuff. Always redo it. This is a cubic. This is a parabola. Parabolas are going to be easy. Downward facing. Always helps to actually get the minus out of there. And it will give you clearer insight into some things. Yeah, that's fair enough. That does not have a factor. Or does it? Yeah, no it doesn't. And then this one, now find, yeah, so just go back to this step, because you don't need it. So just be aware at t is equal to 0, so essentially s of 0 is 10. And then the first derivative, and acceleration. So acceleration is a constant in this one, and velocity is a line. Farthest left, farthest right for t. So you need to figure out when it's hitting and when velocity is equal to 0. So when velocity is 0 here, t is 3 seconds, which means if it's a downward facing parabola and it doesn't start at 0, 0, it starts at 0, 10, goes up, and at 3 seconds it hits a max, so you'd figure it out. So it's minus 9 plus 18, so that's plus 9 plus 10. So you got 318, 319, sorry. Okay, the problem is it's not going to hit here because it started at 0, 10. It's going to hit when this is 0. And as I said, unless I'm asleep at the wheel, minus 10 has 2 and 5. It does not add up to 7. And 10 and 1. So you'd have to take the quadratic function to see when it's hitting the ground. And I think maybe that's what they want you to do. Number 10. No, which one is this? So you can tell I'm getting tired. It's number 13. Yeah. There it is there. So there's the constant, and there's the velocity. And then initial position of 10. Yeah. Yeah, there's the peak that we figured out. There's a downward acceleration, which is a constant, determined there. There. So you had to use the quadratic formula to figure out what hits the ground. And there's only one time that's positive, so you can reject the negative because it doesn't have a pure factor. Kind of mean of them, but it's just labor intensive. You're going to find the other one probably is easier. Okay, so this one's a cubic. It's upwards facing. At 0, minus 9. You could take one measurement to the right to figure out if it's going, up or down if you wanted. But let's just use some logic here. If this is 1, we don't get rid of it. Same with it, minus 1, we don't get rid of it. If it's 2, we're going to get 8, minus 24, minus 9, we don't get rid of it. If it's minus 2, we get minus 8, plus 24, minus 9, we don't get rid of it. I mean 3, 27, minus 36, maybe minus 3. Minus 3, we get minus 27, plus 36, minus 9. Bingo. So when t is minus 3, when t is minus 3, it crosses the line. And then if I wanted to, no, was it minus 3? Yeah, minus 3. If I wanted to figure out any other factors, I can do the synthetic division. And again, I didn't do it right. So this comes down, minus 3, add it. I did something wrong. I mean, minus 3 isn't it? Minus 27, plus 36, minus 9, minus 3, is it? So what am I doing here? This is what happens when you're super tired. A plus of a minus should be minus 15. 3 times that is going to produce plus 45. Was it 3? No, it's minus 3 because it makes 27. This makes... Oh no, it don't. I got it all wrong. It doesn't work. My bad. 27 with 3 minus 36 minus 9 also doesn't work. My bad. So there's no point. Minus 3, sorry. Stupid. Sleep at the wheel. Anyway, let's just take the derivatives. And the second derivative. And by the way, when velocity is 0, or when this is equal to 0, you'll find an inflection point if you really want to see where it's turning. So you can set this easily to 0. So t is equal to 2. So t is equal to 2, you're going to get 8 minus 24 minus 9 minus 33, 25. That helps. I put the wrong point here. Yeah, I'm really tired. Minus 9. So it's going to go up. Boy. T is equal to 0. There's an inflection point at 25, which means... Was it 8 minus 25? So it's going down. Yeah. God, I'm just screwing this up entirely. So it's 3 in the morning, in case you're wondering. So at least I now know it's heading this way. It hits a bottom and goes out. So the bottom is going to be when this is equal to 0. So 3t squared is equal to 12. T squared is equal to 4. When t is plus or minus 2. So 2 there and 2 there. There we go. Then you can figure out the peak. And if you want to make sure that it's downward facing, this should be a negative when we get minus 2 into this, and it is. And it should be a positive when we get plus 2 into this. No, it's 0. Ah, so it hits the graph. It hits the graph at 2, 0. Which probably means... like that. So minus 2... Oh no, it doesn't hit the graph. I'd have to plug it into the thing. 2 is 8. Oh man, I'm tired. Yeah, it doesn't hit the graph. It's way down here. And where it crosses, I don't think it's crossing in normal spots. But now you could definitely have the inflection points if you wanted, and other things. And the extreme positions furthest left and right. And they're saying t is equal to 0. So we know we're not, I shouldn't have bothered with this stuff. So minus 9 goes down to a bottom point at 2 seconds, which is like minus 8, minus 25, so 2 comma minus 25. And it comes up, crosses here, keeps going, and I mean, and as far as this right, we know ends up in positive infinity for a cubic graph. Yuck, I butchered that one, and that one's super easy. Sorry. Oh, number 15 is stupid and a waste of your time, but anyway. Number 14 is straightforward. I'll show you some tricks to 16 and 17. But it's never going to be on a test, so don't worry about it. It's for other people, doing more advanced stuff. So this is a to the power 5. And will the acceleration be 0? Okay, well, when the acceleration is 0, you'll have to determine velocity if it's moving away from the origin or towards. Okay, so let's find the first derivative. So that's velocity. Let's find the second derivative. That's acceleration. When is the acceleration 0? When that's equal 0. So obviously it's going to be t squared cubed is going to be 1 because 20 goes to this side. Here, I'll do it out for you. So when this acceleration is going to be equal to 0, so when time is 1, so that's when acceleration is 0, time is 1. You now have to punch it back into the velocity equation, which is up here. So you get 5 minus 20, and you discover a negative 15 velocity, which means its slope is downwards, which means it's moving away. Okay, so at t is equal to 1, there's 0 acceleration, and it's moving away because the slope is minus 15 meters per second. I believe that it'll say all that, I hope. Yeah, right there, very quickly. So I'm going to show you how this isn't as hard as you think, this 15. Okay. But it's arduous. So you just got to treat all these k's like numbers. Show that the acceleration is constant. Easy enough. That part's easy. So what's this one? 2kt. What's this one? It's going to just be this number, because this is just t. So this is velocity, right? This disappears. It's not part of it. Now we're going to do acceleration. So this is 2kt, so just get 2k. That's just a number. It's gone. K is just a number. There's no t's in there. So acceleration is equal to 2k. K is just a number. Let's say it's 1,000. We can see that's constant. So it's very easy to prove that. Find the time which the velocity is equal to 0. Okay, so here's what you do with that. Determine the position. So when you set this to 0, you're going to isolate t. So all that's going to go to the other side. Okay, which means t is equal to this. You'll instantly see that this goes into that, and this goes into that. So you're left with 3k minus 5. So that's a time. And I know it doesn't look like a time, but that's the only time you're going to get. And then when you want to answer this part, you are now going to, wherever you see t, there, and there, you would plug it in with your new time. Okay. So you get k, and you know, I really don't want to bother doing this, but it's just a long expansion. And then you get this thing times that thing, it expands through, you got to add the 2k. You go on and on and on. You just don't screw up your numbers and your expansions, but you're going to end up with something with k in it. And you can see it's not that hard, it just takes time. Just takes a long time. So yeah, there you go. Right. So you can, let's see if we got our velocity right. Yeah, they didn't even cancel. Oh, we forgot our plus 2k on, yeah, we forgot our, oh no, it's right there. Why do I have it as plus? It was multiplying before. UKT set to 0. Oh, they're just giving us the equations. Yeah, they're proving that. And then they're here. There we go. Yeah, we got it right there. Oh, why did it have minus 3k? Oh, yeah, sorry. It had the minus in front of the bracket. So there's a great example of not doing proper writing. So the minus would have turned this into positive. So yeah, sure enough that. But look at this long answer. See? They just expanded it and grouped and added their like terms, etc., etc., etc. So if you keep accurate, nice line things, you will not make these mistakes. It's just, I'm trying to show you how to do the problem. And that's pretty much it, because the part C stuff is not the stuff I want to focus on. I'm trying to focus on tests, but I'll give you a couple hints on this one. And, you know, don't waste any time on this if you're just trying to barely pass your test. Focus on the fundamentals. This one, forget it. That one drove me nuts. This one cheats. This one cheats. So the secret of this one, the velocity is given in terms of time. And they want you to show that the acceleration of the object is a constant. So you got to take the derivative of this, but so you got to look at it like this. And here's the secret. So you got to do the chain rule. So when this becomes negative, right? And then it's got to multiply this, anything that's multiplying speed, because this is just a number. They just tell B and G are constants. So the derivative of the content is just this part. So you get times 2G, and that's the secret. So this means, this with this negative means this. And it's the same as this thing here. Right? Because this negative just says, take it down, square root it. And this 2 is part of the half. And this 2g is the derivative of the inside. B just disappears, it's a number. So up here you have 2g. Now here's the trick. Didn't up here they say velocity is equal to this? So this here, oh yeah. And the derivative of speed you have to take. And what is the derivative of speed? A derivative of speed is velocity. So I forgot, because they did it in terms of distance, not time. Which means you have to turn the derivative of this part into 2g times velocity. So you end up with 2g times velocity. But down here, you're allowed to replace it with v. Because that's what that is. They told us that in the beginning. And right here, you can see the 2's cancel out, and the v's cancel out, and you're left with g-force. That's what they're going on about. As far as this Newton's law, if you can do it, power to you. I kept doing it, and I was not getting what they were getting. But I'll tell you one secret that I believe to be true, which makes it chaotic, is at some point you're going to have to convert this into this. And that's because, well, this is down here, and I think, yeah, as a square root at some point. This, technically, let's see if I got that right. Yeah, I think I'm going to have to do it. If I'm going to end up with 3, I forget the technique, but essentially you're splitting this up, and if it's to the half, if this is to the half, right there, the square root here, you can rewrite it as, instead of to the half, it's to the 1, and the half's at the top. Because if you use your rules of exponents, this is the same as saying x to the half over x over x. So if you had the same base, you would subtract the exponents. What's negative a half minus 1? It's negative a half, which just means x to the negative half, which just means that. So re-expressing that into that is part of the solution. The other part of the solution is that this gets converted to the term acceleration, and then there's a whole bunch of cancellation going on, but for the life of me, I couldn't figure out the